Hello again. In the last class, we talked about the basic assumptions of the Drude's model or the Drude's theory. Uh, so coming into this class, as I do always, I just recap some of the things from the earlier class. So let me just recap what I just said in the last class, which are the basic, your basic assumptions of the Drude's theory. First assumption was as the electrons move out randomly, they undergo collisions, but there is a definite time scale between two successive collisions, which is denoted by tau. Tau is the time scale between two successive collisions. And if you observe within a time dt, the probability of an electron undergoing a collision is dt by tau, which is probability of collision is your dt by tau. Only when dt is less than tau. This dt or this this probability goes to 1 if dt is greater than tau. Dt is greater than tau. Naturally, if you are looking beyond the time scale tau, then within that time it has undergone a enormous number of collisions and its motion has randomized, and the net average momentum, which the thing that naturally follows from this is the net average momentum becomes 0. All right. So the motion is completely randomized and the net average momentum goes to 0. The probability of collision is given by this. That probability of collision is dt by tau. Fine. The second assumption was the electrons move about randomly. This is just a reiteration. Randomly undergoing collisions. They move in straight lines with a constant velocity between collisions. Okay. So between two collisions, they move in a straight line with a uniform velocity. And the moment it undergoes a collision, that time is much lesser than what it takes to undergo a collision. All right. So the motion is randomized between collisions, but in between two successive collisions, it can be affected by an electric or magnetic field. When suppose it undergoes a collision. Suppose the electron undergoes a collision. In traversing from its initial point to the point where it undergoes another collision, in between these, it can be affected by electric or a magnetic field. Okay. Of course, I want to say that the force it exerts on the electron, it gets affected by the electric or the magnetic field. The force they exert, it affects the electron. It affects the motion of the electron. The momenta can change between two successive collision when it gets affected by an electric or magnetic field. So the momenta of the electron can change between collisions due to the influence of an electric field or a magnetic field. All right. Force it exerts on the electron that can affect the moment. All right. Now the third point was, the third assumption was, we are working the dependent electron approximation regime. The electrons in the electron gas are non. All right. So they have no interaction between themselves. There's only kinetic energy, there's no potential energy, and this is called the independent electron approximation or the free electron approximation. All right. So please just go back to the earlier lecture and just read in details from very good book like Kittel, like Ashcroft Mervyn, these assumptions, and try to get it in your head very clearly. With these are the basic assumptions of what we are starting to read about the Drude's model. All right. So these were the three assumptions. Now we ask the question. Now we ask the question: are we can we be able so can we find the momenta at a time at a later time dt from a time t? We ask the question that what is the momenta at a later time dt from a current time t. So we want to know p of t plus dt from its current momenta, from its current momenta of the electron p of t. So now we ask this question. To answer this question, you have to think about that the electrons undergo collision. So you need to take account of those electrons that have not undergone a collision in this time dt. All right. There's a probability, there's a definite probability that we know from the base first assumption of Drude's theory that dt by tau is the probability that an electron has undergone a collision in time dt, and that time dt is less than tau. Otherwise, it's only 1. So you have to take account of the fact that the electrons undergo a collision, and only those electrons will contribute to the momenta which has not undergone a collision. All right. So you have to give a certain weight to the momenta, and the weight is carried by the probability. So now uh, only those fractions which has not undergone a collision will contribute to the momentum. All right. Now, so P of P plus, sorry, seems all equal. Hmm. P plus T is equals to P of T times probability of no collision. So from first assumption, probability of collision is given by dt by tau, provided dt is less than tau. So probability of a collision not occurring is simply 1 minus dt by tau. You can relate this probability with the fraction of electrons that has not undergone a collision or has undergone a collision out of the total number of electrons, and only those fraction and only those fraction will contribute which for those electrons which has not undergone a collision. So E of t plus dt is equals to P of t at a later time, at an earlier time t times 1 minus dt by tau. All right. So now you can ascertain that this is correct, as because when you put dt, you put you put dt by tau to 1. That, that means that you are looking at a time scale which is greater than tau. By that time, the electrons has undergone an enormous number of collision. Electrons have undergone an enormous number of collisions, and dt by tau is 1. So if you put dt by tau is 1 equals 1 in the above equation, then p of t plus dt becomes 0. And you can recall that the net average momentum because of this randomized motion becomes 0. So now you are getting it back there, because if you are looking at time scale which is greater than tau, by that time it has undergone number of collisions, so the net average momentum becomes 0. So the net average momentum becomes 0. All right. So the weightage you have to associate is because of the number of electrons or the fraction of electrons that has not undergone a collision in the time interval dt that you are looking at. In the time interval dt that you are looking at. So picture is like this. This is P of t, and it is on its way to undergo another collision. So in this time interval, dt, you want to look at it how, what is the momentum. All right. You are asking the question, this question, you're asking this question. All right. Now let's go back to our second assumption. All right. Second assumption, we said that in between two successive collisions, the electrons can be affected by an electric field or a magnetic field. In general, a force that can be exerted by the electric field or the magnetic field. So, in between this collision, if the electron uh, gets affected by a force, then the additional moment it carries will be given by del P is given by Ft dt. Simply, as because this comes simply from the Newton's law. The rate of change of momentum is equal to the force. So if it's affected by an electric or a magnetic field between two successive collisions, it will carry an additional momentum due to the applied force. And this comes from the basic Newton's law. P, P, all right. Now, this is from your basic Newton's law. All right. Now, we work out the earlier equation. Now, P of t plus dt is given by P of t plus the additional momenta because of the applied force weighted by the probability that the electrons have not undergone a collision, and only the fraction contributes that has not undergone a collision. Okay, so this can be written as plus ft dt. All right. So let's open the brackets, and P of t minus P of t into dt over tau plus ft dt minus ft square over tau. Alright. Now, if you remember, this tau is of the order of 10 raised to minus 14 to 10 raised to minus 15 seconds. And you're concerned with the time scale that is lesser than tau. So dt is less than tau. All right. So you can imagine dt is even lesser than tau. So squaring it, it becomes even much less. So you can safely drop the last term, which carries a contribution of dt squared, and keep only the linear terms in t. So let me just check if it's recording or not. Yeah, it's recording. So now what you are left with is, right, so P of t plus dt is equals to P of t minus P of t over tau plus ft. All right. Now you can see that you can bring this term, this p term, to the left side and divide it by dt to get the derivative. In time, p of t plus dt minus p of t by equals minus p by tau plus f. Okay. Therefore, dp dt is equals to minus p by tau plus f of. We have come up with the celebrated Drude's model, or the Drude's equation, where the rate of change of momenta, the rate of change of momentum is given by dp dt is equals minus p over tau plus f of t. This is what we have been looking for. All right. If you look into the terms, this term, this term, so this term is just because of basic Newton's law. Which are all familiar with. The rate of change of momentum is equal to the force applied. And the first term is your drag term. This comes because of the collisions. So Drude's addition was that the electrons will undergo a collision and it will generate a drag force that will contribute, or even they contribute positive way or a negative way, but it will contribute to the rate of change of momentum. The rate of change of momentum of the electron is affected by the force applied and the drag term which arises because of the collisions. Now we get back to now as dpdt minus p by tau plus f of t. What if we put ft equals 0? Is 0, implying dp dt is equals minus p over p by tau. Solve it. This is very easy. And by integrating, we get p vector p naught equals to minus d tau. So the momenta exponentially decreases in a typical time scale of tau. If we put this, if there's no force acting on the electrons, they'll exponentially decay down. The momenta of the electrons will exponentially decay down. If I plot it will exponentially decay down, and the time scale tau is the time. This is with t. This is t. So this is tau. This is the time which is the tau is the time by which it has reduced to 1 by e times of its initial velocity or the momentum. So if one applies an electric field, or let's say a magnetic field, an applied force in general, then the electrons will respond to the forces, and it will exponentially, of course, and it will the momentum will change as per the force applied, and there will also be a drag term which arises due to the collisions. And if there's no force applied, the momenta of the electrons will exponentially decay down only because there's the collision. Okay, and as we know that because of successive collisions, the momenta will be randomized and the net average momenta will go down to 0. So This is your all right. Now coming back to the discussion, that we took only the contribution from those electrons which has not undergone a collision. Fraction of electrons not undergoing a collision in time dt is 1 minus dt tau of all electrons. This goes into the weightage factor, and number of electrons undergoing a collision is dt over tau. So the correction factor due to those electrons which have undergone a collision, electrons which have undergone a collision, they are to be taken care of also. But this is a correction factor. Let us see how does it contribute, or it does it contribute at all. So what happens is that the, just after collision with an electron, the momenta gets randomized. That we know. All right. The momenta gets randomized. That means the net, it can be in every direction. So the net average momenta contributing to the momenta that we are seeking, that what is the moment at p at t time t plus dt, there's no contribution from those electrons which has undergone a collision by that time. So the electron was in this position. It has undergone a collision. Now it can go in each direction equally probably. Electron going in each direction is equally, every direction is equally probable. So it will not contribute to the momenta at a later time dt, p of t. Now what is left? So the momenta it has collected, it's only due to the force that is applied since its last collision. So let me just write down the electron before undergoing collision has gathered a momenta due to the applied force since its last collision. So this is the first collision it has undergone, and this is the second collision it has undergone. So since collision 1, it has gathered a momenta due to the applied force, right? And within that time t, the electron has undergone a collision. At most, the time dt can be tau, okay? Because beyond that, every electron has undergone a collision, because you have said that the net time scale, the typical time scale for the typical time scale between two successive collision is tau. Beyond that, every electron has undergone a collision, and we are looking at a time dt which is less than tau. So now we are looking at the contributions, if at all, from the electrons that have undergone a collision. So uh, so it has gathered momenta from the force applied from its last collision. So the del P in that case, right, the subsequent collision is in that case FTDT, which is natural to say. It's easy. So the momenta is only due to the force applied, and it has to be weighted by the factor dt over tau. So the contribution of momenta that electrons the undergone collision is ft dt squared over squared. I just keep messing things up by writing. Now, so you can easily see that you can safely ignore this term. It is quadratic in dt, which is very small, and squaring it becomes even smaller. So you can safely ignore the contribution from the electrons that have undergone a collision within the time dt. So it does not hamper the equation we got earlier, which is dp dt equals minus p over tau plus f of t. So this is the Drude's equation. And this is the force equation. Only addition is that the drag term is there. This is all additional contribution from the electrons undergoing a collision. Now we are going to specifically review a situation where you apply an electric field. So between two successive collisions of the electron, you apply a electric field. Okay. And you want to analyze the situation, what happens in case you apply an electric field. And for the preliminary case, we are going to talk about a stationary electric field. Static electric field. It's a DC field. Okay. So E is static or DC electric field. All right then. The force due to the electric field is minus E times the electric field. All right. So what we should write is dp dt equals minus p over tau minus E of E vector. All right. So now what you see in a real case, you apply an electric field, you get current. Get current. Now what concerns the current? What mathematical term we get for current in a problem? We talk about the current density. All right. So for current density, we write J vector, as we know, is given by minus N E V vector. N is the density of electrons, number density of course. V is the velocity of the electrons, and E is the charge of. All right. Now to get a constant current across the sample that you are applying electric field to, or current, to get a constant current, the velocity of the electrons need to be constant. Just get this. For getting a constant current, you need to have a constant velocity of the electrons. And what does that mean? The constant velocity means the rate of change of momenta is zero of the electrons. So from the earlier equation, if you are to get a constant current, the constant velocity of the electrons, then surely your dp dt needs to be zero. All right. So now your p by tau is minus E of electric field vector. So to get a constant velocity of the electrons, the drag term balances the force applied by the electric field. The drag term is there to balance the force applied by the electric field, and you get dp dt is zero. That means the rate of change of momentum is zero. Now, this implies that p vector is equals to minus E tau into vector, implying mass times the mass of the electrons times the velocity of the electrons is given by this. All right. Now, v vector is minus E tau by m. All right. But we know that j vector is minus n e v vector. Let's just put this bookkeeping stuff. V is given by minus j vector by n e equals minus E tau over m times E vector, which finally reduces to j vector equals n E squared tau over m times E. Now, if you realize that from Ohm's law, we knew J is equals sigma E vector, right? Where sigma is the conductivity of the. So now we have a form of the conductivity of the material, which is given by n E squared tau over m. The form we have been looking for is the form of the conductivity, and Drude's equation, the Drude's model, give an estimate of that. We can see that sigma is equals to n E squared tau over m. That is the resistivity. It is m by n E squared tau. Notice that this conductivity or the resistivity is dependent on the time scale tau, which is the average time between two successive collisions, net time between two successive collisions. So from the equation of motion of Drude, deriving from Drude's assumption, Drude's model, we have now an estimate of the sigma, which is n squared tau over m. All right. So let's just stop here, and please go back and go through the basic assumptions, read it carefully, and try to follow the steps we have done today. That given force, given an applied force, we can have an estimate of the conductivity of the material. It's just a basic equation of motion from the Newton's law, basic Newton's law, with addition of the drag term that comes from the collisions. And to get a constant current across the sample, you have to have a balancing term that opposes the external force, and the balancing term that contributes, that contribution comes from the drag term, which arises from the collision between the electrons. All right, balancing those terms, we get that the sigma or the conductivity is dependent on the number density, the square of the electronic charge, the mass of the electron, and most importantly, the time scale between two successive collisions. All right. And we also clarified that even if we take the contribution from those electrons which undergo collision in the time interval dt, it it doesn't alter the our basic equation of motion, because the contribution is of a dt squared form, which is negligibly small. So let me just stop here and thank you.